right, so 1-4, we are going to build functions from functions. Do you remember fog and goth?
Yeah.
And 3-4, f of g and g of f? So we're going to do a lot of that stuff today. So the only thing that's really kind of new for you is considering the domain. And so you've already considered the domain. We've looked a lot at that. And so we're going to take that and input it into here. So I have given you the sum, difference, product, and quotients of functions. And those are fairly simple. You're just going to take two functions, add them together, subtract them, multiply them, and divide them, and simplify as needed. But then they're going to want the domain. So things that restrict the domain are what? A denominator, right? So if you have a variable in the denominator, so that implies that highly possible when you divide two functions, you're going to have a restriction on your domain. So look for that. What else restricts domain? There's one more thing. Square root function. Right? So if you have something, a variable underneath the square root, your domain is going to be restricted as well. So those are the two main things that tend to restrict domains. So let's look at number 1. I was going to say, if you're digging out another U of A, you got another thought coming. All right, so better not have it out. You might have the same thing happen to it. So f of x is equal to x squared, and g of x is the square root of x plus 1. So we're going to find f plus gf minus gf times gf divided by g and g times g. Plus, we have to also make sure you read all the directions. We have to give the domain of each of those. So let's start with f plus g. So A, I have f plus g, and we put that in parentheses of x. F plus g of x. So I'm going to take the f function, which is x squared, and I'm going to add to that the g function, which is the square root of x plus 1. Can I simplify that at all? No, I really can't. I can't add those at all. So that is the answer to f plus g of x. Then we have to consider the domain. Does x squared restrict the domain? Nope. What about the square root of x plus 1? Yes, it does. So how does that restrict the domain? What am I going to do? What am I going to do with it? What do I set it to? 0. Not 0. That would be a domain, or that would be a denominator. Greater than or equal to 0, because I can take the square root of 0, which is 0. So I want to take from my domain the x plus 1, and I want it to be greater than or equal to 0. Then solve algebraically, so you've got x is greater than or equal to negative 1. If I were to graph that on a number line, wouldn't it be a closed circle at negative 1 and an arrow to the right? So how does that look in interval notation? My boundary point is negative 1. What's the leftmost boundary of this? This is at negative 1. Infinity is the right bound. Right? Infinity is going towards infinity. So wouldn't your leftmost boundary point be negative 1? And do we include negative 1? Yes. Yes, because it's equals to. And then we go through infinity. So our domain for f plus g of x is negative 1 to infinity. And let's just check this on our calculator. Let's take that out. Let's put in the glare off. X squared plus the square root of x plus 1. Right. Isn't it starting here at negative 1? And if you're not sure, you can go to your table, second graph, and if I put in 0, I get 1. If I put in negative 1, I get a value. And if I put in negative 2, all of a sudden I get an error. That's to the left of negative 1. So definitely it's not an asymptote, because an asymptote, negative 1 would not count. It's not a whole, because if it were a whole, negative 1 would not count. So here's what's making the x squared parts making that curve up. All right, so let's look at subtraction. How does that change the graph, and how does that change the domain, if at all? So part B, f minus g of x equals, so I'm going to take my f function, which is x squared. I'm going to subtract the g function, which g comes second, and that is the square root of x plus 1. Can that be simplified? Can I actually subtract those? Nope. So that's my answer for the subtraction. Has the domain changed, or is it the same? The x squared isn't going to affect anything, but this is x plus 1, same as it was in A, right? The domain has not changed, has it? It doesn't matter. We're not going to distribute the negative into the radical. So I would still be setting x plus 1 greater than or equal to 0, so the domain has not changed. The domain is still negative 1 to positive infinity, and let's just double check on the calculator. So this was the original graph for the plus. Let's see how that graph changes for a minus in between. The graph becomes much more like a J swing, right? And it's lower. But doesn't it still start at negative 1? Sure enough. So the domain has not changed. So then let's look at multiplying. So if I take f times g of x, I'm going to take the two functions and just multiply them together. This times this. Doesn't that look like x squared times the square root of x plus 1? I cannot distribute the x squared into the radical. I can't simplify this any further. That is the answer. And again, isn't the domain the same? It's the same thing underneath that radical. Nothing's changed. So our domain continues to be negative 1 to positive infinity. And let's check how that looks on the calculator. So that was our graph. So let's take out the subtraction. Now it's kind of in between the addition and subtraction graph. Does it start at negative 1 still? Go to infinity. No. All right, D. Let's divide. F divided by G, if I made G in there, of x. So I'm going to take my f function, which is x squared, and I'm going to divide it by my g function, which is the square root of x plus 1. So we still have, can that be simplified? It can? Oh, you're thinking of rationalizing it, right? Yeah, don't worry about rationalizing. Once we hit pre-calc, we put rationalizing so much, apparently it doesn't become as important. From an algebra teacher's perspective, it does bother me, I will say. All right, so that cannot be simplified. The same thing is still underneath the radical, so it appears the domain is the same, except it's not. Why? I'm still going to set this to something, but can it be equal to 0? Can the denominator be equal to 0? Because if underneath here we get the square root of 0, what is the square root of 0? 0, and you cannot have 0 in the denominator. So I can't have x plus 1 equaling 0, but I can have x plus 1 being greater than 0. That's fine. And so x is greater than negative 1. So all that does is it changes it to an open circle arrow to the right on that number line. And so how does that change how the domain is written? Right, you're going to have a parentheses, not a bracket. Very good. So don't forget that denominators can't be 0. There's only two things you have to remember about restrictions on domain. And then the last part is g times g. So g times g of x. So I'm going to take the square root, here's g, the square root of x plus 1 times the square root of x plus 1. What does that equal? Just x plus 1, right? Can't be simplified. What do you think the domain is? Mr. Buckner, you're actually correct. But you're just guessing. Do you know why? Can you explain why you're correct? But most students are going to look at this. Normally, if I gave you this, is that restricted? X plus 1. That's not restricted. But you have to remember to look. You must look. What color do I want to do? You must consider the original function prior, bless you, to simplifying. If I just put x plus 1 on my calculator, it's going to plot the equation x plus 1. But if I put in parentheses square root of x plus 1 squared, look what happens. So if I put parentheses square root of x plus 1 and parentheses squared. Oh, that's not what I want. Take that out. X plus 1 and parentheses squared. That's what I want. Look what the graph looks like. It is a graph of a straight line going through the y-axis at positive 1 with a slope of positive 1. But where does it start? At negative 1. Because, so you don't see the left part of that graph. Because for your domain, we still have to take that x plus 1 and set it greater than or equal to 0. Because in the original function, there is a restriction on the square root. So we still get x is greater than or equal to negative 1, which gives us the domain as everything else has had here, except for that part B up here, negative 1 to infinity. And if you forget that, we're going to have an answer choice on MathXL for negative infinity to positive infinity, which is normally what that domain would be, but because the original had a square root in it, it gets restricted. If you put to check it on your calculator your simplified form, your calculator is going to support your decision because the calculator doesn't know that to get this, you started off with the square root of x plus 1 squared. Well, we're not going to go into that right now. Are you looking at the less than, greater than? Yeah, but it doesn't cut off the graph. Yeah, it just shades it, and then you have to shade, and it's not really inequality. You can't really tell your calculator to cut off that part of the graph. So you have to be smarter than your calculator. Okay? Unless you have a Casio, they'll do everything. Certain Casios. All right, so then let's look at compositions of functions. That's your fog and your goth. If you remember from last year, f of g fog. It's really not an O in there. But that's composition notation, or g of x. All it means is we're taking the f function, and normally, you know, we said we're going to add the functions together here and just keep the x as is, but this is normally f of x. Whatever's in here, we will replace every x in the f function with that. So what's inside here is a g of x. So it's saying take the f function and wherever you see an x, replace it with the entire g of x function. Not just x, but the entire g of x function. And the same thing over here. You're going to take the g of x function and wherever you see an x in that function, you're going to replace every x with the whole function f of x. So it can become complicated. Let's look at example 2. Our two functions are f of x is e to the x, and g of x is the square root of x. We're to find fog and goth, and verify numerically that the functions are not the same. I'm going to show you graphically, as well as somewhat numerically. You just have to reason your way to it. So let's start with fog. So f of g of x is equal to. We're going to take the f function, which is e to the x, and I'm not going to put parentheses here because it's not really necessary, but it would be e to the x. Wherever the x is, I replace that x with the entire g function. So I am taking all of this and putting it in for just the x. And so I get the square root of x up here. So there's my answer. Notice that they don't ask for restrictions. But there would be restrictions on the domain here, right? X cannot be what? Or X must be what? It's a square root, right? So what do you set this to? We just did it. What did we set it to? Guys, cannot be that short-term memory. Don't you set that greater than or equal to 0, right? So X has to be greater than or equal to 0. If you put a negative in there, you can't take the square root of it. But they didn't ask you for that because you'll see why when we do GOF. All right, so GOF, G, of F of X. Oh, I forgot that on the other part. Sorry. All right, so we're going to take the whole G function, which is the square root of X, and instead of X, this time we're replacing the entire F of X into that X for the G of X function. Taking the whole G of X and putting F of X into there. So that becomes e to the X inside. Replace that whole X. That can't be simplified. So there's your GOF. Technically, this is unrestricted because X can be positive, negative, it can be 0. Because the base is positive, we saw this when we graphed the e to the X function, it's always a positive value for Y. And so you're taking the square root of a positive value. This particular one has no restrictions on the domain. Now, how do I verify that the functions are not the same numerically? Well, let's just try to get them into the same look, so to speak. This is already a power, isn't it? Base with an exponent, right? Let's get that to be that. If you recall your power rules, let's just say I had, 2 to the 5th, and then I had the cube root of that. Isn't that equal to 2 to the, you take 5, whatever the base in here is raised to, put that in the numerator of the fraction, and the root goes in the denominator? Agreed? All right, so I'm going to do the same thing here. So I'm going to take my base, which is e. It's being raised to the x, so that goes in the numerator of my fraction, and the root is square root, so 2 goes in the denominator. So this is really e to the x over 2. This is not e to the x over 2, because if I try to take that square root away from there, use the same theory, I've got e to the x inside is raised to the first power over square root is 2. This is e to the x to the 1/2. This is e to the 1/2 of x. So I could also write this as e to the 1/2 x. These are not the same. So this is a more complicated example than you most likely would have, but those are numerically not the same. You can check it graphically as well. We're going to put both of these into the calculator. So I'm going to put e. Your e is above your division symbol. So second function, division. I'm going to raise that to the square root of x. If I graph that one, that's what it looks like. Notice that it's being restricted to greater than or equal to 0. Then I'm going to put this one in. This one's the square root of e to the x. So watch that one. That one, as the e to the x, the exponential one, is hugging the x-axis, so it has no restrictions. But are these graphs exactly the same? Nope. So graphically, they're not the same. You can write yourself a note on there that you could also prove it graphically and show that the graphs are not identical. There'll be a time where this would be important to know if they're the same, and we'll get to that later. All right, so let's look at another one that's doesn't have the e in it. So I'm going to do GOF with you and have you do the fog on your own. So note that it's been switched around. You're asking me for GOF this time first. So that means I want to take the g function. So I've got the g function, which in this case is the square root of x. I just write the square root with a blank x. Wherever there's an x, in this case there's only one x, I replace that x with the entire f of x function. So x squared minus 1. All of this goes into that x underneath there. Notice that what's inside is the f of x, what's the outside is that g of x, because you're going to have to go backwards in the next example. So then they want you to also find the domain of the composite function. This is the composite function. That can't be simplified because x squared minus 1 becomes x plus 1, x minus 1. It's not a perfect square. You cannot take the square root of it. Each one of these individually are, but as a whole you can't take its square root. So, what are you going to do about the domain? Say that again. No, I can't pull out an x. That doesn't have an x. You cannot take the square root of x squared and take it out front because there's a subtraction sign. It has to be all multiplication before you can take the square root. So, say that again. X squared minus 1 greater than or equal to 0. Right? So I'm going to take whatever's underneath there and set it greater than or equal to 0 because that's the restriction. It must be greater than or equal to 0. Now, I would not suggest that you add 1 and take the square root of both sides because 9 times out of 10 you forget to do the plus minus. There should be 2 answers here. So this factors into x plus 1, x minus 1. And I'm just going to revert to equal 0 because we're going to use our number line and our checkpoints to determine what it really looks like. And then doesn't x equal, if you set those equal to 0, negative 1 or positive 1? So those are your boundary points. So we're going to check them in the original. So something to the left of negative 1, I don't know, negative 5. So if I check negative 5 times negative 5 is 25, minus 1 is 24. Can I take the square root of 24? Yes, it's a positive number. It's not a perfect square, but it's a positive number. I can take it. So isn't that true? Right? So then in between, what's a great number in between? 0. 0 times 0 is 0. Minus 1 is negative 1. Can I take the square root of negative 1? No. Not without using I. So it's false. Take a number to the right of 1. 5, so do 5 again. So 5 squared is 25, minus 1 is 24. Can't I take the square root of 24? So it's true. And isn't it equals to? So if it's looking like this, I need to have a line over the true part with an arrow, and a line over the true part here with an arrow. And I filled in the circles because it's equals to. So I need to show that as an integral notation. What is my leftmost number over here? Negative infinity, and my rightmost positive infinity. So as I start from the left, I hit negative infinity, so my domain is equal to negative infinity to negative 1. Is it included? Yeah. Then what do I put? A u. And then over here, I start with 1. It is included, so bracket to positive infinity. So there's your whole domain. Not that much different than what you've been doing. Right? Now, if we graph this, we can check. Actually, graph your composite separately. We've got x squared minus 1. And then we've got your square root of x. And then the composite is the square root of x squared minus 1. So here's the first graph. That's your x squared minus 1. There's your square root of x. And here's the composite. What does a composite look like? Absolute value graph, doesn't it? Isn't that fascinating? So let's take the other two away. Let's take that one away. And let's take that one away so you can see it. Almost, but not quite, right? It's missing, isn't this the part between negative 1 and 1 that x cannot be? Yeah. It's really a curved line rather than a straight line. But that's an interesting graph. You do fog. So it's in reverse. You start with f, and wherever there's an x for f, you put the g function into f. So you do it on your own. Let's go. Wake up. Then I also want you to find the domain. Yep, you need to actually square, simplify it as you can. You can't leave it that way, because you can actually square that. We don't exactly cancel out the square. Yes, so now find what it equals. Keep going. Yes. Then I want you to discuss with people around you what you think the domain is. Emphasis on think. So chat, chat, chat. Chat with somebody next to you. No, he's not next to you. You got Quincy next to you. You've got Ellie next to you. Miss Murray doesn't count. All right, so what is the composite function? Do we all agree that it's x minus 1? What's the domain? Is it all real numbers, or what did you say? Negative 1 what? To positive infinity?
No, 1.
No, but you're close. Now, here's the deal. Remember what we've been talking about. No, yeah, you can go ahead. No, but you're close. Come on. What? Because if I square the square root of x, it just gives me x, and it doesn't affect the minus 1. No. Well, that's what they're trying to do for domain. What is the only thing that's restricted here? If you look at this and put this into your calculator, what are you going to get? You get a line, right? But that's not the proper graph. Your calculator doesn't understand that to get that, you squared the square root of x. So if I go back and change this to the square root of x squared minus 1, look at the graph now. Where is the first x value that you come to? No, x value. What's the x value at this point? 0. Remember, we go vertically with our hand, vertically from left to right. Aren't we cutting the x-axis? So we're thinking x ordered pair, right? The only thing that's restricted here is this square root of x. So to get your domain, you just take the x and set it greater than or equal to 0. That's where the restriction comes from. And so your domain is including 0 to positive infinity, because the 1 here has nothing to do with it. Or some of you put a 0 in here, I think, and then found the value at that order. Or you looked at your graph and found the value of that ordered pair, and you're like, oh, the graph's down here at -1, 0, -1. Domain is x values. So we want the x value of that ordered pair. Does that make sense? Because the leftmost point is this one, and that ordered pair is 0, -1. What's the x value of that ordered pair? 0. So the very smallest x that you can have is 0. That's what I just did here. Algebraic, I took what was underneath the radical, which is just the x, and I set that to greater than or equal to 0. That's how I went from here to here. If this had been an x plus 1 underneath here, I'd be an x plus 1 greater than or equal to 0. Yeah, it's the same thing that we did in example 1e, right? You had to look at the original equation to get that restriction. Okay, last two problems. So for some of you this is going to be hard, for others of you it's going to be super easy because it's just how your brain is wired. You're given the h function, and you're to break that h function into f of x and g of x. This is the composite function. They've done FOG or GOF. Okay, so we're assuming it was FOG instead of GOF. So they want you, and that's what you must assume. They want you to, well, and that's what they're saying here, aren't they? they're saying that h of x is f of g of x. Isn't that fog? If they said g of f of x, that would be golf. So what they're saying is they've taken the f function and replaced every x with a g function. So the g function is on the inside. Look at this function h of x. Is there something that's on the inside that repeats itself? X plus 1. That's a real clue that when you have something that looks somewhat complicated, that both of those are on the inside, right? So that must mean that what's on the inside of that x squared in the parentheses here, that must be the g of x. This must be your g of x that they have put into place. Because what they did was they took, originally, f of x must have been what? What must have f of x been? What here? Not x, but cover that up. What do you see? Something squared. That something squared must have been an x squared, because didn't they replace every x with a g of x? And then cover this up. That's minus 3 times something. That something is an x. It's plain x. Plus 4. If it helps you to think of this in terms of, that's a u squared minus 3u plus 4. U squared minus 3u plus 4 is no different than x squared minus 3x plus 4. Do you see that? Some of you are like, yeah, others are, and it has nothing to do with intelligence. It has everything to do with how your brain is wired. So what did they put inside of x squared and x? X plus 1. So g of x must be x plus 1. And this is a skill we're going to use later on, tearing apart that composite to its separate parts. So that's all you have to do for that one. I want you to think about b. What do you think f of x is for b, so think on your own, and then what do you think g of x is? Look for something that's inside an overall something else. And this particular one, you could consider it 2 different ways. Mm-hmm.
F of x is x squared, square root of x, and g of x is x to the plus 1.
So he is saying that this is what's on the inside of something overall. That overall something, if I just cover that up, is the square root of something. So that's the square root of x. What's on the inside is x cubed plus 1. That's a simpler form. That's what Math Excel is going to want. Did somebody else come up with something else that you thought it could be? Okay, so the other one, so this is or Brendan said that f of x was the square root of x plus 1, right? And then all we did was replace the x only with x cubed. Could that work? Yes. Probably, I'm telling you, probably, and you'll have to tell me if this is not true, probably this is what Math Excel is going to be looking for. I'm not sure if Math Excel is going to accept that answer, because I didn't think of it that way, personally, and so it wouldn't have occurred to me to think of it that way. So I didn't test that answer out in Math Excel. But you could test it. You have 5 tries, right? You just test it, just to be cantankerous. And then you can come back and tell me if it'll take it or not. So, on a test, I would totally take that, because I can understand where you're coming with that. But generally, this is what we're thinking of. All right, so then do C. Everybody should be able to do C. Are you ready to do it? Give them a minute to think. Hang on. This one you really can't have 2 different options. Quincy, what is f of x?
The absolute value signs and then x is in the middle.
Very nice. So f of x is the absolute value of x. So Ellie, what's g of x? Go ahead. Oh, what'd you get for f of x?
I would put x outside inside it would be x minus 2.
Wait, you did what? You did what?
Absolute values.
Oh, and you put a 3x in there. Oh, okay. Yeah. Yeah. But I doubt that's what Math Excel is going to want. Do you see what I'm saying? They're going to want 3 minus 2x. So what some of you have done was this. F of x is equal to x minus 2. And then you said g of x was equal to 3x. You could do that. I would still be thinking this way if I were you. Because in the future, this way is going to be much simpler, probably. I would get in the habit of trying to do it this way, although I applaud the out-of-the-box thinking. No, I would not mark this wrong in the test because the Math Excel might mark it wrong, and that's why it's your job to figure it out. Oh, by the way, I've cut down your homework severely. I know you're really sad about that. You only have 13 problems. So if you feel that you need more than 13 problems, you can go into the study plan and take a little quiz over that section. You can always select similar exercise, can't you, whether you got it right or wrong. You can always choose a similar exercise when you practice it. You got 5 chances. So if you feel that you're just not, on a particular question, you're just not there, then you can use those. And I'll leave that up to you because you're big boys and girls, right? Right? Okay. So I purposely went through your homework and cut out things that I thought were multiple duplicates. All right, because I know that I do get annoyed when I take a math class and it has online homework and I'm like, I have it, I understand it, I don't need to do it anymore. After we're finished with this chapter, I'm going to play with the study guide or the study plan thing, which could be good or bad for some of you. For some of you, if you get the concept, it'll automatically cut your homework out, and then, because that's your study plan, you've proven that you've understood it. But if you don't do well, then it'll increase and give you more problems. So you have to tell me how that works, because I certainly don't want you spending, 2 or 3 hours doing homework. I know you don't want to spend that time. So we'll play around with that, maybe on maybe on a chapter, and see if you what your thoughts are on that. I don't know. It might be a good thing. It might be good for you to try to get it right the first time. Get it right the first time, and you have less problems to do because it'll automatically cut out problems like I just did. So if I assign 23 problems, you could only end up doing 10. Does that make sense? Yeah, it'll count for 23 because it gives you the percent. All right, so last example. Determine which of the ordered pairs 2, -5, 1, 3, and 2, 1 are in the relation defined by x squared y plus y squared equals 5. And then you have to determine is the relation a function. So make sure that you read all parts of the directions. And you cannot put this in your calculator because it's got a y and a y squared. So we're going to take each ordered pair and we're going to just plug and chug. So we're going to take 2, -5. Its x value is 2, the y value is -5, and we are just going to use substitution. So notice that I am putting parentheses in for my variables x and y. I'm going to replace x with the value of 2, and these are both y, so they get replaced both with -5. Now on my test, you're going to have to prove it, so don't stop short of proving it. The problem with Math Excel is that it's not grading your showing of work. I could click that, by the way, and make you have to show work. You're welcome. But that means that you have to pay attention and study your notes for things that I say that you need to be able to do. So for instance, we're going to chug through the math. 2 squared is 4 times -5 is -20. Plus 5 squared is 25 equals 5. If you stop there and say yes, I will count it wrong. If you haven't proven it to me yet. 5 equals 5. You should not be adding or subtracting things to both sides. We're not trying to solve anything here. We're just seeing does the left side equal the right side. Since that checks, this is a solution to that function. Well, may not be a function. To that relation, because we don't know if the relation is a function. So now let's try the second one. So 1, 3. where my x value is 1 and my y value is 3. So we're putting in 1 for x and 3 for y. Follow your order of operations. 1 squared is 1 times 3 is 3. So you shouldn't get a 9 there. But you should get a 9 here. It's 5. Don't stop. Keep going. What equals what? 12 does not equal 5. So that is not an ordered pair in the relation. And then the last one is 2, 1. So there's our x and our y. So I'm putting in 2 for x and 1 for y. So 2 squared is 4, times 1 is 4, plus 1 squared is 1, is equal to 5. So again, don't stop short. 5 equals 5, you're proving it. It checks. So those are the 2 ordered pairs out of the 3 that they gave you that work. The question is this relation a function? Yes or no? Now you can't graph it, so you can't use the vertical line test. What's left? How do you determine it? No, negative x would only tell us if it's even or odd, right? So what can I do to remember that ordered pairs, Seth? There is a repeated x value, very nice. So if there's a repeated x value, is it a function? No. So you're going to write 2 things down because I would totally accept, no, it's not a function. The relation, that sounds really smart, is not a function because the x values repeat. I'm totally happy with that. Or, this is what Math Excel is going to throw at you, so I thought that you might want to write this down, just so that you recognize it when you see it. Or, the ordered pairs have 2 different y values. There's an E in there. Y values for the same x value. That's a little bit more wordy than the x values repeat. They're both saying the same thing, but I wanted you to recognize that that is saying the same thing as the x values repeat. Do you have any questions about anything we talked about? Seth?
You're talking about the variable number of questions that we do in Excel, study plan.
Oh, if I clicked on the study plan.
Yeah, but how would that work if we have questions about a certain number?
Once as you go through it, they have each question broken into